Good morning, everyone. I am back with another video for lesson 1.8, still for calculations in analytical chemistry, but this time we have a different set of topics. So this time we have two targets. First, to outline the preparation of solutions, and second, to perform stoichiometric calculations. So to start, what solutions have you prepared in the laboratory before? Have you started with solids? Have you prepared solutions starting by dilutions? Or have you ever prepared buffer solutions? So in this section, we will go into the calculations involved in the preparation of solutions. So I'd like to show you this illustration for preparing solutions from solids or probably by dilution. So in the first illustration, you can see that after weighing the solid, you would have to transfer it to a volumetric flask, which is already about half filled with solvent. And then step 3 is to dissolve the solid by swirling. And then finally, to add the solvent until the final volume, as indicated by the mark on the volumetric flask. So notice that this is the proper way to prepare a solution. It's always prepared inside a volumetric flask, never on beakers nor on Erlenmeyer flasks. And also, we are supposed to make sure that all of the solute has been dissolved entirely in part of the solvent before diluting it to mark. Also, if you would like to prepare a solution somewhere that is not in a volumetric flask, it should only be in the intermediate steps. Like for example, if you'd like to dissolve your solid in a separate container like a beaker, you'd have to do it in the beaker and then transfer it on a volumetric flask and then make sure that the beaker that you have used would be washed with distilled water and the washings added to the same volumetric flask to ensure that you have not lost any of the solid intended to be part of the solution. Okay, so we can also prepare solutions through dilutions, that is, starting from a more concentrated stock solution and diluting it into a less concentrated final or standard solution, which you would actually use. So the formula for that is, from the module, the volume of the concentrated solution times the concentration of the concentrated solution would be equal to the volume of the dilute solution times the concentration of the more dilute solution. So V times C equals V times C. Probably in your previous lessons, you were more familiar with V1 M1 equals V2 M2 or M1 V1 equals M2 V2. They're the same thing. For example, describe the preparation of a 2 liter of 1.0 molar sodium hydroxide solution from a 4.00 molar sodium hydroxide solution. So following that formula, we simply have to substitute on the more dilute side 2 times 1, and on the more concentrated side, we have the unknown volume times the 4 molar concentration of the stock solution of sodium hydroxide. And then simply transfer this 4 molar to the other side so that the final answer for the volume of the concentrated solution would be 0.500 liters reported in 3 significant figures. Also, this is not the final answer yet, because going back to the solution, remember that we are asked to describe the preparation and simply not to report what volume of the stock concentration is used for the preparation. So to answer the question, this is our final answer. We take a 0.5 liter volume of 4.00 molar sodium hydroxide and dilute it to 2 liters with distilled water. And the result would be a 2-liter volume of a less concentrated solution or a more dilute solution with a concentration of 1.0 molar. Okay. Next, how do we prepare buffer solutions? So these are very special, if you can still remember, because they resist pH changes despite dilution or the addition of acids and bases. So these are usually prepared from a conjugate acid-base pair. And this equation is very important when dealing with buffers, the Henderson-Hasselbalch equation, with this form, pH equals pKa plus log of the molar concentration of the base over the molar concentration of the acid. For example, calculate the pH of a buffer solution prepared by mixing 0.2 molar formic acid and 0.5 molar sodium formate. The Ka of formic acid is 1.8 times 10 to the negative 4. Notice and remember that Ka has no unit. So simply using the Henderson-Hasselbalch equation, we can substitute the values for Ka, 1.8 times 10 to the negative 4. Also, the concentration for the base, in this case, it comes from sodium formate, 0.5 molar. And in the denominator, we use the molarity of the acid, 0.2, to get a pH of 4.14. This is the final pH of the buffer prepared in this manner. Also notice the final number of significant figures. So here, because we will be use 0.5 over 0.2 gives us, after this operation, we should be getting only one significant figure, and then after getting the log, it should be in with 1 decimal place. And then here, so for this problem, we should have only 1 decimal place. However, I would assume that the given here should be 0.20 molar and 0.50 molar. That is why this has been reported with 2 decimal places in the final answer. Next, how do you prepare a 500.0 ml buffer solution with a pH 4.5 from 1.0 molar acetic acid and sodium acetate, given the Ka of acetic acid? So using the Henderson-Hasselbalch equation, we solve for the only thing or the only quantity lacking in the Henderson-Hasselbalch equation, and that would be the concentration of sodium acetate. So for the pH, we are given its value. For the Ka, we are also given its value. And then for the concentration of the acid, that's 1 molar. So we are looking for the missing quantity, which is the concentration of sodium acetate. So manipulate the formula on your calculators. Try doing some practice. So you start with 4.5, then you add the log of 1.8 times 10 to the negative 5, and then you get the anti-log, meaning you press shift log of the answer that you're getting on your calculators, and then multiply it with 1, or supposedly whatever number you get from here, you'll get the concentration now of sodium acetate. And that should be 0.569 molar. And then to calculate for the mass of sodium acetate, we start with 0.569 molar, or expressed in moles per liter, and then we'd have to convert it into grams because that's the quantity that we would have to weigh. So we multiply it by 500 ml expressed in liters, and then we convert the moles of sodium acetate to grams sodium acetate to get the final mass of solid that we will have to weigh. So the solution is prepared by weighing 23.3 grams sodium acetate, dissolving it in the 1 molar acetic acid solution. And then the pH is checked and adjusted by adding small amounts of acid or base as appropriate. So notice that when we dissolve it in the 1 molar acetic acid solution, we are expecting that the final volume of the buffer solution, which already includes the 1 molar acetic acid solution and 23.3 grams sodium acetate, would be 500 ml. And then also, again, let me reiterate that the final answer is not this number, but the description of how the buffer solution is prepared. So again, the buffer solution is prepared by weighing the solid sodium acetate, dissolving it in the 1.0 molar acetic acid solution, diluting to mark until 500 ml. The pH should be checked and adjusted by adding small amounts of acid or base as appropriate before diluting to mark. Okay, so that's it. Next, stoichiometry. It allows us to establish the quantitative relationships among elements in a compound or among chemical species involved in a chemical reaction. So this is the general flow or scheme of interconverting between mass of one substance to its moles, to the moles of another substance, and then to finally the mass of another substance. The stoichiometric ratio here found in the middle is based on the balanced chemical equation. Therefore, it is important to always check whether the chemical equation involved is balanced correctly. So if we're going to interconvert the mass of an atom that belongs to a compound, then we do not need the stoichiometric ratio coming from a balanced chemical equation. Rather, we'll just look at the number of atoms of that element present in the chemical formula of that compound. Example, what mass of silver nitrate is needed to convert 2.33 grams of sodium carbonate to silver carbonate? And what mass of silver carbonate will be formed? So this is just one problem. So we start with writing the balanced chemical reaction. So sodium carbonate plus silver nitrate forms silver carbonate plus sodium nitrate. But the product that we're interested of is the silver carbonate. So we'd have to convert 2.33 grams of sodium carbonate fully. That means the mass of sodium nitrate that would be needed to react completely with it can be solved stoichiometrically. So we start with the mass of sodium carbonate and then multiply or divide by the molar mass to convert it into moles of sodium carbonate. Then use the mole ratio from the balanced equation where 2 moles of silver nitrate is equivalent to 1 mole of sodium carbonate. And then after that enables us to convert everything into moles sodium nitrate, then convert it into grams sodium nitrate using the molar mass of silver nitrate. Again, we finally convert it into grams of silver nitrate by multiplying it to the molar mass of silver nitrate and then do the computations. Okay, so the final answer for that would be, for letter A, would be 7.47 grams. Okay, it's here. To answer letter B, what mass of silver carbonate will be formed. So you can start with okay. You can start with this same solution. Then instead of converting it into silver nitrate, you can just convert it into silver carbonate. So the mole ratio is just 1:1, and then multiply it by the molar mass of silver carbonate to get this answer. 6.06 times 6.06 grams silver carbonate. Now, where did this come from? The 0.02198. Okay, so that would be, yes. So this actually comes from this part, 2.33 grams sodium carbonate converted into moles sodium carbonate by dividing with the molar mass of sodium carbonate, and then using the mole ratio of 1 mole sodium carbonate react producing 1 mole of silver carbonate. So that's 0.02198. Okay, so that is where this comes from. However, I would advise you, if possible, that in all calculations, it's better to start with something that is given. So instead of starting with something that is already an intermediate result, okay? Practically, I would advise that because it eliminates possible errors. Like, for example, if this answer is not correct because you have done an error previously, then that makes everything else wrong. So it would be better in all your calculations to start with something that is really given from the original problem. So again, you can start with the 2.33 grams of sodium carbonate, then divide it by the molar mass of sodium carbonate to get the moles of sodium carbonate, then convert it into silver carbonate, 1:1 lang naman yung ratio, and then multiply it with the molar mass of sodium carbonate to get, molar mass of silver carbonate to get grams of silver carbonate. And the final answer is 6.06 grams in 3 significant figures. So still related to the same problem, what mass of silver carbonate is formed when 25 ml of 0.2 molar silver nitrate are mixed with 50 ml of 0.08 molar sodium carbonate? Okay, this is a different problem, although it's a familiar reaction, sodium carbonate and silver nitrate. Okay, sodium carbonate and silver nitrate. So we still have the same chemical reaction, but what's the difference this time? Notice that in the previous problem, we are dealing with masses. So we're given the mass of one reactant and the mass of another reactant. They are reacting to form a precipitate, and we are also concerned with the mass of the precipitate. On the other hand, in the next problem, notice that we're not given masses anymore, but rather we're given the volume of a solution. So our reactants we aren't looking at the masses of solids this time, but we're looking at the volumes of different concentrations of solutions. So sodium carbonate would be a colorless solution. Silver nitrate would also be a colorless solution. And then we mix them up, they form a precipitate. Silver carbonate would probably be white. So just imagine that we're mixing a colorless solution and another colorless solution. When they come in contact with each other, they'd form a cloudy solution with a um, precipitate falling out of the solution. So first, we'd have to determine the limiting reactant. So in the previous example, notice that we were only given the quantity of one reactant and assumed that it has reacted completely with the corresponding amount of the other reactant. This time, we are given the quantities of both reactants at the same time. So if we're given the quantities of both reactants at the same time, we should not assume that they react completely. Merong isa na nabigay ng mas madami compared to another reactant that was given in a limited amount. So we'd have to determine which of them is limiting. So to do that, we'd have to get the available moles of silver nitrate and the available moles of sodium carbonate. And to get the available moles, that would simply be taken by multiplying the volume with concentration. So 25 ml multiplied with 0.2 moles per liter. You can immediately use millimoles per ml for the molarity, or in this case, they would prefer the answer to be in moles, therefore the ml was converted into liters before multiplying with the molarity. And we do the same for in order to get the available moles for sodium carbonate. And then we got these. Next, the amount of silver nitrate that will react with sodium carbonate will be here, starting with 25 ml sodium nitrate, convert it into moles sodium nitrate, then using the mole ratio, we convert it into moles sodium carbonate, and getting 2.5 times 10 to the negative 3. Now we compare. This is the number of moles of silver nitrate. This is the number of moles of sodium carbonate. If all of the silver nitrate were to react completely with sodium carbonate, it would be reacting with 2.5 times 10 to the negative 3 moles. But in solution, we have 4. So, comparing them, we can infer that only 2.5 times 10 to the negative 3 moles is required to completely react with the available silver nitrate that we have. Therefore, we actually have an excess of sodium carbonate, which is, we can do arithmetic. So this would be 1.5 times 10 to the negative 3 moles. We actually have an excess of 1.5 times 10 to the negative 3 moles of sodium carbonate. So, since the amount of sodium carbonate that is needed to react with the available moles of silver nitrate is less than the available moles of silver carbonate, then we can say that sodium carbonate is the excess reactant. Thus, silver nitrate is the limiting reactant and will determine the mass of silver carbonate formed. So, we're going to start our calculations with this, the number of moles of silver nitrate, converted to the number of moles of the product, and then use the molar mass of the product to get the mass of the product. Okay. This is what we do to answer the question, what mass of the product is formed. Okay, so again, this problem has used the 5 times 10 to the negative 3 mole silver nitrate, copying it from the previous calculation that we already had. Okay, coming from here. However, again, I would advise that if it is possible, you always start with a given instead of copying results from intermediate calculations. So there. The final answer is expressed in 3 significant figures. And then there's a follow-up question. What will be the molar concentration of sodium carbonate in the solution produced when those two quantities of the reactants are mixed? So we calculate the excess number of moles of sodium carbonate left in the solution, okay, like what we showed earlier. So the excess number of moles would be 1.5 times 10 to the negative 3. Then we calculate the molarity of the solution by dividing the total number of moles of the excess reactant with the total volume of the solution after mixing. So that's 50 ml plus 25 ml. Converted into liters, so the final concentration of sodium carbonate would be 0.0200 molar in 3 significant figures. So that ends the lesson. We have 3 problems for the navigate part. First, describe the preparation of 750 ml of 6.00 molar phosphoric acid from the commercial reagent that is 86% weight per weight and has a specific gravity of 1.71. Okay, so we would have to this is a dilution problem. So we would have to convert first the 86% of stock solution into molarity. Okay, so after converting this into molarity, using the density or the specific gravity, we can then calculate for the volume of the more concentrated stock solution that we will be using. So this converted to molarity will be like M1. Then we are looking for V1. And then this will be M2. This will be V2. For number 2, what mass of sodium formate must be added to 500 ml of 1.0 molar formic acid to produce a buffer solution with a pH of 4. So simply use the Henderson-Hasselbalch equation, get the concentration of the base to get the desired concentration of the formate ion, and then from the concentration, use the volume to get the number of moles, then convert it into mass using the molar mass of sodium formate. Number 3, exactly 0.2220 grams of pure sodium carbonate was dissolved in 100 ml of 0.0731 molar HCl. What mass in grams of CO2 were evolved? You'd have to write the chemical equation first. Sodium carbonate reacting with HCl, most likely 2 moles of HCl forms NaCl, CO2, and water. Okay, so balance that equation first, and then you are given the quantity of sodium carbonate as well as the quantity of HCl. That means that this is a limiting reactant problem. So you'd have to get the number of moles of reactant 1 and the number of moles of reactant 2, compare them, and express reactant 1 in terms, first assume that, let's say, the sodium carbonate reacts completely. So convert it into the number of moles of HCl, check which one is greater. Okay, so that you'll know which one is limiting and which one is in excess. And then finally, what is the molar concentration of the excess reactant? So this problem almost exactly follows the scheme that we did for the sample problem that we have discussed earlier. So that is all for Navigate, and that is all for the lesson. Again, I hope that this has helped you digest the module. Bye, class.